Hey guys, today I will be presenting a research paper called Music2Video. The authors of this paper are Jang, Sumin Shin, and Yoonjeon Kim. They're all from Korea Advanced Institute of Science and Technology. The aim of this paper is basically to create a music video given the lyrics and the song. So that's text and audio. So VQGAN stands for Vector Quantized Generative Adversarial Networks. It was first proposed in the paper Taming Transformers by University of Heidelberg in 2020. So it combines convolutional neural networks, traditionally used for images, with transformers, which is traditionally used for language, and it's great for high resolution images. Whereas CLIP stands for Contrastive Image Language Pre-training. It was proposed by OpenAI in January of 2021, along with GPT, but I think only CLIP was open sourced. It's a model trained to determine which caption from a set of caption best fits a given image. So in essence, these two networks work with each other. Like they work in a way where VQGAN generates the image while CLIP judges how well an image matches our text prompt. This interaction guides the generator to produce more accurate images. You can see in the picture right here that VQGAN says city during a rain night and Clip says no, not really. And then it actually generates a pretty believable picture. And I guess Clip is then happy with it. All right, multi-modality with Clip. So learning common representation of image and text using contrastive objective has gained great attention for its versatile usage in text-guided generation and manipulation of image. So CLIP and its variants consist of two separate encoder networks, one for each modality. For a pair of positive multimodal samples, that means if the text and the audio are talking about the same matter, then the contrastive learning framework attempts to minimize the distance between the different modalities while pushing away the unrelated samples. In simple terms, CLIP is a model trained to assess the fit of a caption compared to the other captions in a set to an image. It is capable of zero-shot learning, enabling it to perform well even on unknown data. Recent work extends the representational ability of CLIP into audio using diffusion, which is what we're calling wave to CLIP. The shared representation space of image, text, and audio enables the latent code of the GAN to generate an intended image using both text and audio data. So now that we've understood CLIP, we need to understand VQGAN in a bit more detail. But before we can do that, we need to first understand these important concepts that you see on your screen that it all borrows from. And we'll do it in a more intuitive way where we're going from bottom to top. So first, let's talk about a theory of perception. Right. One thing that I like about VQGAN is that it prescribes an explanation of how we see things. What is it that you actually see in this image? So some of you will say it's a white cat looking up. Some of you will just say it's a cat. Nevertheless, we seem to encounter images through discrete representations, cat, white, or looking up. This theory of perception suggests that our visual reasoning is symbolic. We ascribe meaning through discrete representations and modalities. This symbolic approach allows us to understand relationships between different words or different symbols. In machine learning, this is commonly known as being able to model long-range dependencies. Even though a lot of work has been done to explore complex reasoning through discrete representations, most computer vision techniques don't think in terms of modalities. Instead, they think in terms of pixels. They think in terms of large chunks of information. Common CV techniques focus on an image smallest unit, which is the pixel, and what color it represents and the scale of it. Needless to say, this may not be how our perception really works. Despite all of these, we still shouldn't ignore pixel-based approaches. Convolutional neural network, which is CNN, proved that we can model local interactions between pixels by restricting interactions within their local neighborhood, which is the kernel. So this allows us to compose pixels together and learn visual parts. A CNN can learn how to compose pixels at varying layers of abstraction. All right, so now we have two complementary techniques, which is an interesting view of perception that allows us to model long-range dependencies by representing images discretely, and a pixel-based approach to learn local interactions and visual paths. VQGAN was able to combine both of them. It can learn not only the visual parts of an image, but also the relationship between these parts. You can see the table and it summarizes sort of everything. Next, we'll move on to CNNs. Since we've all studied CNNs enough, I'll keep this one short. It's based on the shared weight architecture of the convolution kernels or filters that slide along input features and provide translation equivariant responses known as feature maps. You can see a little diagram doing that. Then the next concept we need to understand are transformers. So on 12th June 2017, Google rocked the research community with the catchy groundbreaking paper, Attention is All You Need, introducing the transformers, a neural network with zero recurrences and just uses the attention mechanism. So the idea of attention is one of the most influential ideas in deep learning. The main idea behind attention technique is that it allows the decoder to look back at the complete input and extract significant information that is useful in decoding. The attention mechanism looks at an input sequence and decides at each step which other parts of the sequences are important. A limitation in the transformer network is its computation scales quadratically with the length of the input sequence because of its attention mechanism. So 4 would become 16 and 16 would become 64. To learn about the long range dependencies between tokens, it computes for the pairwise inner product between each pair of the tokens. As a result, they reduce the context by downsampling the resolution. That's why transformers can't give you high resolution images. VQGAN, though, learns an intermediary representation before feeding it to a transformer. However, instead of downsampling the image, VQGAN uses a codebook to represent visual parts. We'll study what the codebook is in the next slide. The authors did not model the image from a pixel level, but instead from the code words of the learned codebook. So it doesn't start from scratch, it starts from a certain entity. So the codebook is generated through a process called vector quantization, VQ, which is the VQ of the VQGAN. Vector quantization is a signal processing technique for encoding vectors. It represents all visual parts found in a convolutional step in a quantized form, making it less computationally expensive once passed to a transformer network. So the discretized code book enables a transformer model to compute attention between the local features, using the encoder network that maps the original image into the latent space. VQGAN additionally uses the vector quantization process to represent the latent space using code books. Using the discretized latent space, generator reconstructs the latent code into realistic images using adversarial loss between generator and discriminator. So they will take certain features and they'll reduce it to a certain point, and then that is what the starting point is. One can think of vector quantization as a process of dividing vectors into groups that have approximately the same number of points closest to them. Each group is then represented by a centroid, which becomes the code word, usually obtained via k-means or any other clustering algorithm. In the end, one learns a dictionary of centroids, which we call the code book, and their corresponding members. On a conceptual level, we can think of these code words as the discrete symbols that we used in our earlier examples, like cat or white or window. By training them with a transformer, we start to uncover their relationships. All right, at this point, we now have all the ingredients needed to discuss the VQ-GANs architecture. A CNN that takes a set of images to learn their visual paths. By taking advantage of a pixel's local interactions, we can learn high-level features to construct new imagery. A transformer network that takes a sequence to learn their long-range interactions. Given a discrete representation, a transformer allows us to understand a relationship across visual parts. And a codebook obtained via vector quantization. It consists of discrete code words that allow us to easily train a transformer on top of it. However, we'll make a few tiny adjustments. We'll replace the CNN with a GAN, and the layers still perform a convolutional operation, but with a GAN, it synthesizes more distinct visual parts. And secondly, instead of having a separate process for vector quantization, VQ GAN will learn the codebook right away. Learning the feature map of visual parts happens inside the GAN. It's still the same two-stage approach though. If we look under the hood of VQ-GAN's generator, the setup is reminiscent of autoencoders, where the goal is to have a decoder properly reconstruct the input. The theory is that if we have a perfect reconstruction, then that means the encoder has found a suitable representation of the data. So vector quantization also happens between the encoder and decoder networks. So instead of reconstructing from the encoded output, we do it from its quantized form. When put together, we obtain the discrete capabilities of VQ, the rich expressivity of GANs, and then encoding capabilities of the encoder. This allows us to obtain richer and more distinct visual paths than a standard convolutional neural network. Now let's talk about the transformers. Once we have the codebook, so we're only interested with the codebook because it provides a discrete representation of our visual parts that can readily be fed into the transformer. So to do so, we represent the images in terms of the codebook indices of their embeddings. This means that the encoding of an image can be represented as a sequence from our codebook, like white cat looking out of window. So this would just be code words, and now we have a sequence. And now that we have our sequences, we can just train our transformer to predict the next index of an encoded sequence. Lastly, when generating high resolution images, the authors restrict the context via a sliding window. This means that when generating each patch, it obtains information only from its neighbors. It's a nice trick to improve resource efficiency when using transformers. And you can see a little diagram again at the bottom left corner of your screen. All right, BQGAN takes a lot of inspiration from previous works in the field. Here's an attempt to trace how each development led to the other until it collapsed all into VQGAN plus clip as we know it today. You guys can pause the video and read it further if you like. All right, the framework is divided into three main parts. The video scenery transition based on music, which is basically where you want to cut the video so that you want the video to change with the music. So where would you cut it and where, what, like we basically cutting the music into segments. Then we have iterative audio and text guided optimization, which is if the audio says elephant and the text says tiger, which one would you use? How would you diffuse the two? So that's what that part's about. And then time consistency in video generation, which is basically you want any two frames to be consistent in a way where they have a certain flow. It can't just be tiger elephant, like that won't be aesthetic for us to enjoy. So the first part, video scenery transition based on music. In order to create a music video which changes the scenery accordingly with the music, we determine the timestamp where the musical statistics change drastically based on strength of onset. Given the segments of music, we determine frames per second based on the average intensity of the music segment. The given music is transformed into a Mel spectrogram, which shows intensity of each frequency in a decibel for a given time interval. We compute average intensity of each segment and then regularize it between 0 and 1, and then this becomes our frames per second. And we require frames per second because that's what tells us how many times do we need to carry out the image generation and latent code optimization processes. Then we have iterative audio and text guided optimization, which is uh, as I explained, how do we optimize the certain frame, the image into audio generated or text generated, right? The naive way, the dumb way would be to just do it iteratively, like once by audio, then by text, once by audio, then by text. Keep doing that, but that doesn't give you good results. Instead, what they have done is, given a certain segmented section of music, we provide a single guidance for multiple frames in single selection. Since multiple frames correspond to the same number of iterations, each iteration will have the same audio or text guidance for an extended period. To illustrate further, each section is given a segmented audio prompt encoded into a clip vector, and if only the section consists of a timestamp with the given lyric, then the lyric is encoded into the clip vector. Unlike the iterative approach, which alternates audio and text guidance for every iteration, this approach successfully represents both modalities of music and lyrics. And then we have time consistency in video generation, which is based on the created sequence of images, we generate a video that maintains context from previous frames. Since every frame in a video should be consistent with the previous frame, we explain how to maintain time consistency. They use two methods, L1 regularization of latent vectors and addition of guiding prompt vectors. The first approach we experiment is to regularize the latent vectors at iteration t, which is denoted as zt, to have minimized L1 norm with the previous latent vector. And then the second method, so basically the first method doesn't work so well. That's why they use the second method, which shows more consistency, which is to, as you can see in the equation, the second equation, you add the two distinct clip prompts for different frames. Providing a new guidance of adding the two clip vectors showed consistency in frames such as remaining objects from the previous frames as shown in figure 2. So if you see the first example, A and B, you can see that they're two frames, but they're distinctly, like they're quite different. But in the second, C and D, you can see that the fire is around the same place and the people also forming where something look like people. So that's because it's using the previous frame's prompt. All right, now let's quickly talk about the novelty, the limitations and the implications of this paper. This is extremely opinion based, so I could be wrong about things, but feel free to comment and ask me questions or tell me things. So this paper brings together so many different components that the implementation feels fitting, creative, and a smash hit. The following ideas stood out to me: multi-modality, implementing audio along with text and visuals; segmenting audio based on change in music stats; generating relevant images using all modalities by adding the latent vectors; maintaining the time consistency by using previous frames as context. In some frames, the image generated has text written automatically. If you see the video that I'll post, it has text on certain frames. Like this could result in some very interesting lyric videos. Then the limitations. Although the work is extremely advanced and brilliant, it does feel like it is in the early stages in terms of a finished product. Here are a few issues. Lack of consistent entities throughout the video that could gather interest. Like there's no underlying theme or story. Even though the frames are time consistent, the transitions seem quite random. Conflicting behavior of modalities don't give great images. They require a better way to harmonize with each other. Since music consists of varying themes with change irregularly, the created music video should correspondingly change its theme accordingly, which is hard to capture when the music is segmented with fixed time intervals, with beats or whenever the music. So we need to come up with a smarter way to segment the music. And implications. A paper like this definitely inspires new ideas with regard to what you can do with this technology. Here are a few notes and ideas. Applications where users can interactively feed in music source and text source to create artistic music videos. Due to multi-modal representation, we can also input images. Therefore, we could enhance an existing music video by feeding in audio, lyrics, and visual frames of the song. Manipulating the latent space would generate different images, right? So maybe we can create an interface for users like you and I to add and subtract entities in the video. Like, say, example, there's a man and a deer, or some sort of interface which gives you these options. And if you click on a man, now man would stay on the video for the time being. And it would just be as easy as taking a man, just a man latent clip vector, and adding it to the current clip vector. I also understood the significance of using so many different concepts from different architectures and wish to understand how reinforcement learning can be used to better understand a user's preference of videos. If a user could somehow reinforce what he likes and what he doesn't like, and therefore the video goes that way. This is a bit too far fetched, but yeah, whatever. And now let's talk about the Imagenet song. This is a song that the paper has used to demonstrate its framework. It's also called more popularly My Weasel, and it's composed by Yannick Kilcher. The music is divided into roughly 500 segments whose average time interval is 0.6 seconds. On the right hand side, you can see the generated images for a few text prompts. So there's a part where it says, "Be my weasel," and you can see the weasel of sorts. What's inside this wooden chest? You can see a certain wooden chest here. Then "Be my pig." I feel like there's some pig elements, and bring all them to my whiskey jug, which feels very whiskey and jug to me. And also I see some text written in places, which is very interesting because they did not program this just happened. So I'm curious as to what would happen if we actually programmed it to be a lyric music video of sorts.